Okay.
Okay, so
Wang Chao, will you please go to the title? Or if maybe.
okay. So sorry, but just start from this page. Yeah.
Okay.
So today I will talk about I will present one paper, dynamic splicing for deep neural network, and the author is Zhang and Li Yuancheng. Yeah. Sorry for. And the motivation will be so deep neural network is a black box whose decision is hard to interpret. And secondly, which is more importantly, the size of state-of-art deep neural networks and their required computing powers has been growing rapidly in recent years. Thus, it's highly desirable to reduce the size of DNNs to improve efficiency without sacrificing too much accuracies. So how to prune the model effectively. And meanwhile, a smaller model is easier to use on like phones or LOTs or and such things. So that's one motivation. And thirdly, model protections may downgrade the performance, and how to only protect part of model is also important. So the model protection here means that nowadays neural net models are is already a product to sell. So how to keep your model secret is a very difficult problem. Usually the things to do here is that we only open APIs for users to check their plugin instead of providing your models to other people. But to sell, sometimes you need to uh, protect it and give it a key, and then only the one with keys can use your model, but the others cannot. So all this kind of protecting method will downgrade the performance, downgrade the evaluation speed a bit. So the author of this paper is also thinking that if they can protect only part of the model, which is important. So although it will also downgrade the performance and the speed, but the scale is tolerable. Yeah.
So here the model predictions, they have two ways to do. There's more. It's a little bit about the model privacy. So you mentioned that there's the API there. Maybe the API. Do you mean that the API is a cloud API? I mean the model is deployed on the cloud or on the server.
It's so the model itself is deployed on a secure environment and only open API for query.
And also there's some hardware protection. So it's more like I'm not sure when you know the trust computing. The idea is that sometimes the model can be loaded in some encrypted memory. That is still possible. So that means the model, because you know, if we would like to make predictions on real time, the network delay or the network latency will always be a problem. For example, when we Ruofan and I was working on a model, and also Qingzhou is not here. So this model can make the prediction within 0.2 seconds. But if such a service has been deployed on the cloud, the network communications will take 2 seconds.
So why it will take 2 seconds?
Because the network connections, sometimes the network is deployed on the servers, and you start a request, and the server give you a response, and the request and response takes 2 seconds.
Yeah, but actually,
more like when
it's usually not the case if you have a mature server deployment.
It's more like Google. It still takes 2 to 5 seconds to open your Gmail, right?
Yeah, correct.
So the network will have some latency and have some runtime cost. So one of the other way is that we protect the model in the memory, but all the memory is encrypted. So in this case, it still keeps the model privacy, and the user can only know the input and output of the model instead of the model structure and the internal weights.
Yeah.
So so I raised so many backgrounds. I'm asking the question whether the model protection is for both scenarios or just for the cloud API.
It's for local one. So the cloud one usually to protect the cloud one API dealing techniques, this way is not useful. Yeah.
And also, you mentioned that you want to protect a part of the model. And what do you mean to protect the part of the model?
So I'll I'll explain later because it's
Okay.
hard to explain without the background.
Okay, sure.
Okay, so yeah, it's actually without the terminology. So the basic main terminology here is the neurons and the synapse. So yeah, so it's just
Synapse
a
is
brain.
more like a biological.
Yeah, it's a biological. So this terminology is not so similar with the one we learned in CS 3244 or 5242. So to explain, when synapse is a weight, so it's a single weight, just like this one, it's a synapse. This one is a synapse. And one neuron is one operation, like this one. This it's all one operation. But it's not the normal neuron we learned that one neuron consists of multiple weights and one sum, weighted sum, like the one sum and one nonlinear function. Here, the neuron is defined only with one operation.
So from a conventional point of view, one neuron is more like a pack, right? Consists of all the weights connected to it, and the operations and output.
Correct.
Does the conventional definition of neurons contain its output? Maybe, right? We'll say the neuron will have an output. We're always using such a term. Hello?
Hi.
Can you hear me clearly?
No, I can.
Okay, maybe I should leave the micro closer.
Yeah, so that's one. That's why. So this for like so now you should understand the terminology now. So it's the neurons and the synapse, and so the definition of neural network slicing. So the goal the paper want to achieve is like this. So let M equals to N, which stands for the collection of neurons, S, the collection of synapses, represents a neural network, and C, I-O, is a slicing criterion. So C here stands for criterion. So I is the interested model inputs, and O is interested model output neurons. So here, for example, this is samples. So I here means samples, but O here stands for neurons. So for example, there are two outputs here. We may be interested in this output only, or may interested on this output only. So based on this interest output, we can get a set of training. So for example, there are a huge number of training samples, but for this output, there's only like half of them. So this is called interested model input samples, and this is called interested model output.
But the problem is that, so here the output could either be, in this case, I'm not sure my example is correct. To get an output, it could be either 0 and 1, right?
Yep.
And every sample will have, because every sample will have both output 1 and output 2 in these examples.
Correct.
Right. That means, is that possible that we only slice to output 1? Because every input will have slice output 1 and output 2. So how do we cut?
Okay, so in a clear case, suppose this model is a predicting model, and for example, this one is called so this model is to recognize the picture is 0 or 1, for example, and then this model is to recognize the images for 0 or 1, and there are two input neurons. So in the training sample, there should be multiple images, like there's picture 1, picture with 0, picture with not 1 and not 0, like something like this. And if we interested in the label 1 only, so we don't care if this is a 0 or 1 or 2 or 5. So maybe they can select this part, and part of this part to be the interested input sample. Yeah.
Your point is that suppose we only care about the inputs, which will output 1 in here. So by this we slice it.
right? But not, yeah, so that's because I mean that so
Anyways, here are the definitions. But when we go into the definitions, I will have to raise the question of why we need to separate the definitions of the neurons and the synapse.
yeah, that's what will because it's related to how it sliced it. So it's related to the way it actually sliced. So it denotes so the goal of slicing is to compute a subset of NC belongs to N and SC belongs to S, which respect to C. It denotes like this. So yeah, that's that significantly contribute to the value of any output belong to O for any input samples belong to I. Yeah. So that's the definition. So there are a few challenges which are all known. So first, understanding the behavior of each neuron is hard, and it's hard to quantify the contribution of each neuron because output is continuous, but usually we need a Boolean value. So we say that the neuron participate positively or negatively or didn't participate. And dealing with large models are also very hard. So that's the challenges. So the basic idea of the paper is it used 3 phases to select the slices, so which consists of the neurons and the synapse, which called the profiling phase, forward analysis phase, and the backward analysis phase. So it's quite like the neural net training, but it's not. The idea is similar, but the way is not.
I'm not sure whether the paper presentation is used. I still haven't built a link between minimize the neural net or optimize the neural optimize the neural network size and the slicing. So I haven't built a very strong connections between.
Okay, so actually the title of the paper is called Dynamic Slicing for Deep Neural Networks. And the goal of this paper is to slice the network is the proposed way to effectively slice the deep neural network. So actually it does not relate to model repair or something like that.
Yeah, so but the point is that they just would like to slice, but in applications and you mentioned their motivation. You mentioned there's motivation that we can minimize the neural network structures, and you also means that we can protect a part of the neural network model. So for now, I haven't built a strong link between how slice or cut the network can contribute to these two applications.
Okay, so
definitely slice will make it smaller, but making it smaller, we still need to make the network accurate.
Yeah, right? So that's how this will do. It will use 3 phases to select the slice. So image sample will be like this. So the first profiling phase will compute each neuron's average activation module. And then it will feed the interest samples to models and calculate the action value here. Then it will use an algorithm to based on this neuron's reaction to get this final slice. And the one with red label is the final slice they choose. And this one the model with reduced size. But I will also go deep into it one by one. So the profiling phase. So it's quite simple. So it will feed all training data into the model and compute the average activation value of each neuron. So here, so now the active neurons are not only the one after the red loop, but the one for the reduced sum and the red loop. So actually, one neuron can be split into a model like this. So previously, the neuron is like this. So the first half is sum, and the sum is red loop. But now we can actually represent it with the equivalent model is like this. And this is sum, and this is a weight of 1, and then this is a red loop. So this one, so using this technique, we can easily represent our original MLP as the one model that is mentioned in this paper. Yeah. So the actual value of both these are actually recorded. So
it also record the value before ReLU, and the reason might be ReLU might to move a lot of the negative value as 0. So he would also like to provide those negative value before time disappeared by.
Because you have also mentioned that the negative value may stand for some information, right? Yeah, so, and the average values are used as the baseline to understand the reaction of each neuron to specific data samples. So the average of these neurons activations are recorded. And secondly, we'll feed the interest data samples, like the sample we want to compute the slice width, into the model and record the activation value of each neurons. And then the difference.
So how do you define an interested base sample?
So basically the model is so maybe I'll jump to the application first. So here, for example, in application 1, adversarial defense, then the interested models will be the adversarial samples and the normal samples. And for application 2, model pruning, the interested samples will be the one with, so the model pruning here means so normal model prunings will reduce size for all output labels. But for this one, it can be applied to only a few of output labels and discard all of them. Like, for example, in here, the interested examples will be the input training examples for these images. For input training samples for these interested output labels. And for application 2, model protection, and the interested image will be the models, will be the images that related to output that is more private. Yeah, that's how they define it. So it's more important.
So anyways, there are always a few interested samples, and those interested samples are specific for certain tasks.
Yeah, so it's specified for different tasks, but they are so it's called interest data samples. Yeah. And then record the activation value of each neurons. And the difference between the recorded value and the average activation value computed in providing phase represents the neuron's reaction to the data sample. And the magnitude of the value difference indicates the sensitivity of neuron regarding to the data sample. So back to the image here. So we can see that this 9, so in this sample, the average value is set for 0 for simplicity. So you can see from after the forward analysis, we compute that the neuron for this green, the output of these green neurons is 9. So actually, it stands for that the magnitude is 9. So it's quite powerful.
So the number in the cycle means the activation value, right?
Yeah, the first is the average in the providing phase, and this 9 means the value in forward analysis.
It's still an average, but it's an average. The average activation values for those interested samples.
I'm not sure, but I believe it's not the average, but for individual samples.
For individuals, so it is just for.
And the contribution of individual samples are finally summed up as the final contribution. Yeah.
Okay.
So for this one specific input sample, like 1, 2, this is the reaction, and then the 9 is very far from this 0, but this -3 is a little bit close. Like that's the idea. Yeah. So that was the forward analysis phase 2. And finally, and most importantly, the key part is
please keep going on.
Is the backward analysis phase. So The neurons with higher sensitivity are not necessarily more important to the slice criterion. So the slice is initiated with output neurons specified in the slicing criterion, so the selected output neurons, and then it will iteratively analyze each neuron in the slice by calculating the contribution of its preceding neurons, and the preceding neurons with higher contributions are added into the slice. So maybe looking these words are a bit complicated. So I'll show you the algorithm directly. So this is a neural net model M with NNS input sample and targeted. So how to contribute? So for each neuron belongs to the interested output neurons, we will first edit. Oh, let me just wait for a second. Sorry for, I think it's better to get a picture here.
So I suggest that the slides you can make more animations so that the discussion can be more smooth. You can make animations when preparing the slides.
Yes, but like drawing it will actually easier to control. Yeah. Like for example, as our interested output neurons is here, then we will based on the preceding neurons, which is these two, we'll analyze.
So here, let's redefine. So I somehow still miss a part. So let me raise a question. Anyone can follow. Xiangling, is Xiangling here?
Yes. Yes.
Can you raise an example? Maybe I missed some things. Maybe you can graph it. Can you raise an example in this case? What is the slicing criteria? So how do you understand what is the slicing criteria?
You need to choose some interest input and also specify some output. Here, for example, if we choose input 1 and output 1, and by forward and backward, and you find.
Here you mean input? You mean input neuron or an input sample?
Sample.
Okay, given the input samples and given input sample and their output, we would like to.
Yes. So I think is correct.
Right. So you first calculate the average value for each neuron with all the training data, and then you just choose some specific input and output, and by computing the corresponding neurons, and you compare the value with the average value before, and then you can find out which neuron would
make a difference.
Would be most influential for the input and output you choose. So yeah, that's my understanding.
Yeah, that's correct at the layer at the forward phase, but
backward. Yeah, but I might miss some points.
Yeah, but also one thing mentioned here is that the neurons with high sensitivity does not necessarily impact.
Yeah, and I also feel quite weird, because even though you can calculate the average value for each neuron, but if for example, the variance of all the value, the variance is very large, then the average value.
You mean that even the individual input will actually deviate quite a lot from the average, but it might still within the distribution of the.
Yeah, correct. Yeah, but usually the distribution will be So even I agree that the variance will make a difference, but it's not through it's usually not so high the variance. Yeah.
Okay.
It's relatively so how to say that? So it's relatively robust to this different normal samples. Yeah. So Lin Yun, do you got any questions for before the backward analysis part?
Frankly, I have some doubts about their approach because on the deviations from so their idea is very similar to, somehow similar to what we discussed before, right? We would like to choosing what is the most influential neurons about to repair, and then we get to freeze the other neurons and to train that kind of neurons. So that just more somehow have the similar idea to borrow. But I still feel that I'm not sure whether their approach can work um, so smoothly or.
So maybe you can hear their backward analysis phase to see if.
Yeah. So here, let me raise an example. So can we jump to the application? Let's start with application first. So maybe we can start the first application, birth rate defense. So would you please illustrate it and how the neural network slicing can help to defend the birth rate so that we can have a more intuitive understanding and why this slicing technique will be used for in such a scenario.
So I'm not sure it's a good time to say that or not, but so it will basically compare the model slice for adversarial samples and the model normal samples, and says that the slices is very different as compared with one with normals. So normally how the adversarial sample to attack is to give the image some small perturbations that accidentally triggered some neurons that lead to the models to a very different output, right?
Yes.
So that triggered neurons will be this means that if we use the adversarial samples as interesting input and the predicted value of this model as interested output, then we will get a very different model size compared with one using normal samples with as input and the normal output as output.
I get a point. So their point is that is not to defend the adversary sample. It might be to using the slice the subnetwork as an indicator to quantify the adversary.
Yeah, correct. So it does not need to defend, but so it will run this model once and it will get a neural network result. And based on the this slice, it will give a confidence score that it's adversarial sample. Not so it does not so related to the original model anymore. So it can be applied to any models. Yeah. So it can even try another neural net classifier on the slices generated as a helper model. So to see this new NN classifier will be the input will be the neural network slice and the output will be the confidence score or like the prediction or something like that. Yeah, that's the idea.
Okay, let's keep back to the. Let's go back to the forward. I have one more question to ask.
Yeah, can.
So here, the difference, you mean the difference between the recorded value and the average. So I would like to have the graph. Will you please give us the graph? Give me the graph, and I can do mark something there. Yeah, the graph. So this is the version for all the samples, right? So it's more like
this for all the samples.
So basically, they do not. So here they do not focus on. They focus on both neuron and synapse, right? So
Yeah,
neural means the activations and synapse. But the synapse has been, and how do they define synapse?
it's a weight.
It's a way. So, but when the model has been trained, the synapse has been fixed.
Yeah, after the model is trained, the synapse has been finished.
Okay, so basically they just compute the output of the neuron or the activation value of the neurons. And when they apply the forward analysis, they just would like to recollect or, so it's still a kind of profiler, right? It's still kind of profiled, but they're using different inputs and giving their predicted outputs. They still, it's more like the second stage, it means the forward analysis. So they still do the profiling twice.
Yeah, correct. Yeah.
Right? So they actually do the profiling twice. And how they perform the differential analysis.
So that's what is done in backward analysis.
Okay, so the differential is using the backward. For now, despite
so it does not contain differential, but the difference. So the difference of the result is considered as the sensitivity of.
But the difference, every neuron have a difference, right? Every neuron, the activation of every neuron will have a different output.
Yeah,
so they just calculate the slice based on the difference.
So how to calculate the difference is quite important, right? So how to use this difference is important. Yeah.
Okay, please keep going on.
So the backward analysis phase. So the model will be like this. So for this one, so the candidate neurons is the two green neurons that precede this neuron. So it's these two. But how to select this? It's got an equation. So it's called compute the local contribution of n as contribute, and update contribute with this. So this big contribute is a global value, which is numbers, and so it counts. So 1 or 2 or 0 or -1. And this small contribute is a value. So is a continuous value, which is computed by the operation contribution graph defined here. So for different neurons, like the weighted sum, for like this in here, there are also different like average, maximum rectified scale. They all define a local contribution for each kind of value and how to compute it. And based on this computation, it will update this global contribution based on the sign of it. Notice that it's set, but considering that some contribution may be small.
So what's the difference between contribute NL and SL?
I beg your pardon?
There's two contribution. Contribution is a count, right?
Yeah.
Contribution is a count, and what is the difference between two variables? And this NL and SL.
Okay.
NI or SI.
Oh, so okay. So so the literature here, NI means the ice neurons that precede neuron N. SI means the ice synapse preceding neuron N.
Neuron N. Or synapse, S or synapse or neuron.
So S means synapse, N means neurons. N here means the preceding neurons, like if this is N, this is N1.
Preceding neuron, what's the difference between preceding neuron and an interesting neuron?
There's no interest in neurons.
I mean, there must be an output neuron.
Yeah, at first, you can see from the initialize this O as and for all the interested output neurons, it adds this to this, and now this is the interesting neurons.
So it's keep growing the set of O, right?
It's not keep growing, but like you can view this as a BFS.
From the end of the output.
Like for this one, it will analyze this too. And in this stage, it will analyze these three. And in final stage, it will analyze these two, like this, layer by layer by layer.
Okay.
So, if you are not clear, I actually give you provide a sample practice to go through for this how to contribute. So also the key point here is that this one is very important to update. So you can see that it's only consider the sign of it. So actually it will only update the global if the sigma so the absolute value of this contribute is bigger than some threshold, predefined threshold, then it will update this contribute. Otherwise, it's meaningless, right? So like for this one, the two interested are these two, and for this two, maybe.
And how this operation is? So this is more like a union or just update the value. So this is a scalar value or it's a set?
Yeah, it's a scalar value. I have mentioned that this one is a continuous value, but this one is a number value. So it's an integer value. So it's ranging from like -5 or to 5 or something like this.
Okay.
Yeah. So maybe also maybe I can introduce some of this here means. So here means that so contribute n, like for example, this is n, this is n1, this is n2. So n contribution n is like this. For example, with the interest, so at first we'll set all the interested ones contribution as 1. So the delta y here means that the output of this n with the recorded average output. Wi here means this, and delta xi means the difference of the value of this output value regarding to the average output value for neuron n1. Yeah. Okay, so
here when we have these values, we calculate the contribute I.
Yes.
And but if we want to calculate the contribute I, we still need the contribute n.
Yeah, but the n is a layer after it. So I have mentioned that. So we will first compute this layer. So because it's an output layer, for example, these two are all, this the first is interested, the second is not interested, so it's 1 and 0. Then the first iteration will consider this part only. So the value of this big contribute n is these two values, and the value of this big contribute n is these two values. Then I will go to the next step. So now these two are the interested output, and these three are the preceding values. So considering this part, the value of.
But what if we find this value is not interesting anymore, right? So
yeah, then we just discard. Just discard. So the second so the start point of the second iteration of this algorithm will be the first neurons only.
Okay, so let's go back to how they calculate the contribution. So is there the formula for they decide whether a neuron is relevant?
So if the final contribute is bigger than 0.
This is a small one, right? This is a small one.
Yeah, this is a small one, yeah.
This is a small one is greater than theta. So my question is, how do we calculate the small contributes?
Yeah, that's what I mentioned here. So this how they contribute this small contribute.
Yeah, but here there's still a contribute n, right?
Yeah, but this contribute n is in previous layer, which is already contributed, which is already computed.
I see. So from the very beginnings, the contribute n should be contribute 0 or contribute big N, right?
Yeah, at the very beginning, the start point will be the output layer, and if the output is interested, the big contribute of it is 1. Else
so
is 0.
the relevance of the neuron depend on the next layer depends on its next layer. Suppose this one is a questionable neuron. It depends on how relevant is these neurons and the difference between the activation.
Yeah, correct.
And as you mentioned, we split X and Y because we need to have a finite degree of using the WI. And so that means still means that the more different it is from the average neurons, the more it is relevant.
Yeah, correct.
So is that true?
I beg your pardon?
The point is, so the rationale. So when we look into this formula, I think this formula, from my point of view, it can be trivial, as long as we can grasp the rationale. And from these formulas, we can infer that the rationale here is that the more difference it is deviate from the average value, the more it is relevant.
Yes.
And is that assumption true?
The assumption is, from my experience, it is correct. Yeah, from my experience of the
Or is that, or if it's accurate and how accurate it is.
So it does not matter how accurate it is. Just set a threshold that can split the as long as we can set a threshold that can split the
You know that there is a reference. There is the reference and how this reference play a role here. So consider, we will have some input and we will have some output, right? We would like to, so basically we're just doing the model clone, or we are just cloning some neurons. If some neurons, for example, there's more like a TF-IDF. Do you know what is TF-IDF?
I'm not so sure.
So that means suppose this neuron is activated every time when we predicting some output. So this output will be throw away. For example, suppose the idea is that we would like to find the most relevant keyword for a document, right? So
Yeah.
for example, there's article talking about terrorism, and the world Bernardin's 911 event is more relevant. But somehow there's still very common word, which is also very frequent in these articles. For example, the word is the,
Okay.
or the word maybe people, right? Because giving the newspaper, because the news are always about people, so the word people will appear in every article. So
yeah, I think I can understand your question now, and I can explain it. So that's why they record the average. So that's why they record the average value of the activation. If such feature exists, the value in the interesting example will not differ much from the one with the output example. Sorry, the one with the recorded value.
And so here I'm questioning the justification. Do they provide justification why they need to calculate the difference with an average value, and how what does the average value actually means?
So there's only one line.
When we do the profiling in the profiling stage, suppose this value was zero,
Yeah.
and even if this value is zero, or for example, zero will be very special. Let's take 3. And this value will be 3. And 3, and this output value 3 may play an very important role to predict the output neuron is the intrinsic host neuron, and why we need to remove these neurons.
So
here, I think the reference might be useful, but I didn't see how they really, and whether this reference model is used in a proper way. I just have this question.
So normally there's it's not very likely that it will output just like value, resulting that delta xi and delta y equal to 0. So as long as there's some small delta, some small delta, it's fine. Then, secondly, so that's also how they determine this.
So my point that suppose if we would like to giving a few samples and giving the interest output, we may not just need to the reference. Without information of the reference model or activations, we can also include this one into the slice model, right? So so what if we do not using the delta y, we just using the y itself?
So that means like from my understanding, for a neural network model to predict if feature itself is usually a bigger value, but it does not change through different inputs, then its preceding weights will not be very big that give a predicting result.
I'm not sure where given point. My point is here, suppose here is the value, and it outputs a strong value. Maybe it outputs a very strong value here. 5. Suppose it's 5. 5 is very large value. And this large value is determined to contribute to this output, right?
Yes. So so what I mean is that if, for example, although this value output 5, but this can be that for all inputs, this neuron will output value 5. Then it does not make sense to include this neuron because actually for the model decision, this 5 is so.
Yeah, I understand your point, but this 5, that means this 5 is essential for every slice.
It's not. If it's essential for all the
it is distinguishable. It's not distinguishable. I agree that it's not distinguishable.
Yeah, so it's not essential.
But if we would like to slice a subnetwork, it is essential. It is not distinguishable. Just like, for example, what makes a difference between men and women, right? So because there are genes, there are different genes, and only one gene is determined to it determines the gender. But if we would like to have a control and have the whole part of workable or functional individuals, we still need to include something else. Something is not determined or something indistinguishable, but something relevant.
Yeah, I agree that your point, but usually in a large neural network, the situation you have said is usually stands for that this 5 does not have a very small impact to the final output if this feature does not change much.
And also, I was just curious about what if so given the backpropagation or the backward analysis, there will always be some neuron in each layer being selected, right?
Correct.
So the slicing network is actually connected. It will not cause some unconnected network.
So that's why we need this contribute SI here. So so this SI means that the synapse is kept.
But basically, it's still neuron. The neuron is still important. For example, this neuron is in, this neuron is in. This synapse will definitely in.
Yeah, correct.
Subnet, right?
Yeah.
So otherwise, we just remove the.
There's only the case that the one synapse is active, but this neuron is not active. But it does not matter, right?
So that means as long as we can select the neurons, we only keep the synapse between them.
In the final step.
Yeah.
Actually,
so for example, will this synapse still control? Suppose this one is more.
No, it will be removed.
So basically, there's make no point to keep the synapse.
Yeah.
As long as we can count the neurons or determine the neurons, and we can just slice their synapse without during the slicing process.
Correct. So, but it can be the case that something is like this.
Sorry, I didn't clear your remark.
Yeah.
Again.
So it can be such case that and then this is connected, for example. But you can see that this synapse is not connected. So this one is not connect. It's not necessarily connected. Yeah. So that's the slicing one.
Okay.
Yeah. So understanding, I hope you guys have understand how to back propagate. Now let's do a run for calculated. So I'll help you do the first step. So recall that the delta is 20 except for the input layer. So I'll do a mock run to how to select for this particular output. And the neuron here is all some neurons only. So there's no ReLU. So it's only some neurons. Okay, suppose the interest of neurons is here. So by this contribution, and I also mentioned that if
that part is the reference model, right?
Yes, this is the reference model. And then at first, the contributor is 1 because it's output. And the delta yn is 15. And weight is 2. Delta xi is 9. So it will get a very big, 270. So it will get a very big value. So it's bigger than the threshold. So the contribute table will record it +1. And then for this one, it's the same. It's just 1 times 15 times -3 times 1 and equal to -45. And we also see that the magnitude is also bigger than 20. So this one is recorded as -1. Okay, then we have done the first step. So next, I will need to go to the second step. So I'm wondering if someone can help me do the layers with 5 and 2 and 2 in this part. I'm wondering who will willing to take part of this. Note that there's a threshold here. Yeah. So this is the question. So Lin, do you want to pick one or let me pick?
Yeah, I think I can give you a range because Aaon is just enter the meetings, and Ruofan just sent me a message on WeChat that his microphone is not available, and I hope that next time.
Okay, let's Xianglin do this work. Yeah, because Zhengfen seems not here. Let's Xianglin do this.
Okay.
Okay. Let me see. So for this one, I think it would be 1 plus 9 times 9 times.
You're talking about 5, right?
9.
9, it's 9.
9 and like 5.
Yeah, correct.
Times, let me see, 1 times 9 times 1 times 5. So that's 45. 45.
Correct.
And it is bigger than the threshold, so it's positive 1.
Yeah.
And then for this one.
Yeah, the weight is 0, so it's definitely 0, right?
Yeah. So yes. And then for this one, it will be 1 times 9 times 2 times 2, which is also 45. So it's positive 1. And then for this -3, then
you can just say the value. You don't need to.
Okay.
Write it down. Yeah.
Oh, let me see. So it's -1 times 5. Oh no, -1 times -3 times -1 times 5. So it's -15. So it is less than the threshold, so it's 0.
Yeah.
let me recall. So you just like add 0.
Yeah, so you don't need to do anything with this contribution.
Okay,
Yeah.
so and then for the second one, and it's -1 times -3 times 2 times 3. So it's
Yeah.
18. So it's also, 0.
Smaller. Yeah.
Yeah. So and then -1
So you
times
can mark the neurons. So now you work on here, right?
yeah, the second. Oh no, the second one.
The second
it's,
one, neuron.
0. Yeah, and then the third one would be -1 times -3 times -2 times 2. So it's -6. So 0.
Yeah, correct. So yeah,
Yeah.
I think you have like work out how to compute it, and I think most of you got how to compute the back propagate. So I forgot to mention that actually this synapse should be also be marked because it's +1 from here, and this is also need to be marked, and this one is also need to be marked because it's +1. So so understanding this, so we can see that actually the samples it provided is something like this. Yeah, so it's quite similar to the one you work out. Yeah.
But even though I know how to compute it, but somehow
don't know
I don't know the high level understanding of
I do have
this.
I have a concern about his high level.
Okay,
anyway,
what's our concern? You can raise here? Yeah.
The point is the point is just like what we mentioned just now. So this average number somehow may not go
like I don't know what the purpose of this stage, and I don't know.
Which stage?
Like the whole backward backward process. So like this page.
This stage is the key part how to select the neurons and synapse, and so it define a contribution for the synapse and neurons and record it, and it finally.
So like this stage is to determine what neurons would influence the output most.
Yeah,
right?
correct.
Oh.
So like in the first iteration, it will determine 2 of the green neurons, which
I get it now.
Which give a higher input, higher contribution. And why there's a sign here is that, for example, this one gives is -1. So let me think how can I rephrase this. So for example, the contribution is -1 means that this actually give a negative contribution. So if this one also give a negative contribution, actually it's a positive contribution. Because it's negative to negative. So why? So that's why they have to time. So that's why they have this formula here. Yeah. So.
And also one of the points I can raise is that if these neurons, it contribute a negative one and a positive one. So it will be, suppose the theta is small enough, it can be 0, right?
But setting theta equal to 0 does not mean anything, right? So
that means more like a volt, right? Each neuron will have
a volt. Because
if this someone either make a negative impact or a positive impact, okay? So do you think we should
what if the contribution score would be like 45 and -160? So but that would be 0 at last, right?
Yeah, that's still right. And also I have another question is that suppose these neurons make a positive contribution here, and suppose both one are very important neurons, and it make a negative contribution on the above one, and have negative contribution on the below ones. and whether we should neutralize this contribution.
Yeah. So here it does say, it just says that if it only will be considered if the previous one is
neutralized, right? So this case, this will be neutralized, but it is still questionable whether we should consider, because this neuron is very specialized, just like some.
Yeah, I know, but in a global picture with hundreds and millions of neurons, so yeah, so some of special case is tolerable. Yeah, that's what I believe.
And let's do somehow think there's whether there's a simpler way. So we just still do the forward analysis, and we do not do the backward analysis. We just calculate the gradients, giving the input of the inputs, and we have the output, and we calculate the gradients of each neurons to whether they play an important role. And suppose those input have a smaller gradients, we just remove the neurons. Even that is simpler.
Yeah, so that's also one question I mentioned here. So why don't we use gradient as compared with evaluation method mentioned in the backward analysis? So that's also one of my questions. So actually, myself do not get a very good rationale for this, but usually gradient is not good as compared to the feature analysis. So usually the value itself is better. But why we should use the difference of value instead of value itself? My explanation before is that, so if this situation really occurs in a model, it usually means that the weight after it is relatively small, and this feature will give very, very small influence to the final output. So that's what I mean.
I just feel that this paper kind of get lucky to get accepted. But anyway, let's keep going on.
Yeah.
And for example, Wang Chao, so when you read paper, you somehow consider, because we are also analyzing the internal signals of the network to retrain and repair it. So in this case, do you think it will be somehow have some insights or some ideas we can borrow from this paper? What do you think?
Actually, the two aspects are different, but it's hard to say. I have to think more carefully if there's something to borrow. Yeah.
Okay, please go on.
Yeah, but the sign here is we didn't manage to think that. So the one here. So yeah, so that's made something, and also in this paper it also mentioned that if the contribution is negative but the weight is also negative, so it may give a positive output. So the contribution does not only means the weight, but also so the contribution does not only related to the output of neuron, but the weight after this output neuron. Yeah. So that's we need to define train for it. That's I think what's good. What's good to mention in this paper. Yeah. Like yeah. So I hope you understand what I mean. Yeah. For the application, I already mentioned this. So from it believes that and also supports that. But as the experiment, you know that yeah, it only will choose the one that supports its proposal. So it may not usually true, but it's still got some rationale. Yeah. So usually adversarial sample will break some will trigger some unwanted neuron to be activated, causing the final output to be not true. So
I feel that have multiple ways to handle this adversary defense. Majorly, we once after work to check the KL divergence, and it maybe have a better effect for this sliced network.
Yeah, but so the idea here, this paper proposed, believes that the model slice for the adversarial samples and the normal samples are very different, so it can easily distinguish it's an adversarial sample or not. Yeah.
Sorry, I didn't get it when you explained this slides before. So can you like briefly.
That is fine. Wang Chao, you can repeat.
Yeah. So what that 3 pictures mean?
Okay, so there are 3 pictures. The left is not the left, and the right is normal samples, but the mid one is adversarial samples. So it is a train. Sorry, it's a plane, but the predict is dog. So why this situation will happen is that this adversarial sample have some perturbations that misactive or activate some unwanted neurons in the neural network that cause some dog-related features are activated, causing the final output is dog.
So each red dot represents.
Okay, the red dot means the positive contribution of this neuron, and the blue one means the negative contribution of this neuron.
So how can you defend adversarial attacks?
So you can see from it is that, so these two, so usually if it's predicted as dog, there are
one of the most straightforward solutions that we learn, that we just learn the normal.
Yeah, we just know how normal.
Just classifies a sliced network, right?
But that didn't involve any slicing.
The point that we first slice based on the adversary sample and the output.
Correct.
So we first slice the network based on the adversary samples and their output. Right, we just find all the adversary samples which have been predicted as dog. So then we can slice those networks, right?
Right? So you choose. So in the first picture, like you choose the input to be this normal example and the output to be airplane. And the second example would be input would be the adversarial example and the output would be dog, and then you calculate the activation number.
Yeah, and also another way is that maybe we do not even need a classifier. We first slice Wang Chao, when we slice so when we slice the model with the normal samples which has created an airplane, no, maybe that's what we do. What we do is that we first slice the normal example create a dog. So we have sliced the network, right? So then we slice, then we giving adversary samples, because it's still possible that we slice with one sample and with it create a dog. So we will still have another subnetwork, right? So we compare how similar and how different this slice network is from this slice network. This network prime and this network one. And if we can still define the thread hole to see how it is different from it. Then it's still another solution.
Yeah, correct. So that's the first application. And the second application is model pruning. So the rationale is that many pre-trained images model have 1,000 output labels, but many applications only need a few of them only. So how to so the normal techniques are reducing models for all the output, but they do not focus on reduce only a few of output only. So using the model the method proposed, it can do it without retraining and meanwhile reducing the model size. So yeah, that's how it do. So it's just like what we said.
This application it is an experiment. Have you ever done an experiment for that?
It's an experiment, but I just did not provide the percentage of the with
Also, and I also I might miss some points. So by the forward process, you can calculate the influence of the input, and by the backward process, you calculate the influence of the output, right?
The contribution of the neurons to the output.
The contribution to the output.
Yeah, so how do you combine those two together?
So
like the input, the forward.
So the forward and the resulting forward analysis phase is used for the delta y and delta x here in the backward analysis.
Okay.
So it's using the forward propagation, the result of forward propagation.
Okay.
Forward propagation to calculate the
I know.
contribution.
Okay.
So it's an experiment. It does give some accuracy rate with prone ratio and how it actually goes. Yeah, it's an experiment shows that it does. It's okay.
Sorry, let me look at the figures here. So which one is the whole neuron? What is the accuracy of the whole neuron? The blue one? And slicer. The accuracy, okay, and slicer is their proof, right? Okay. The OR is the
No. The slicer OR is choosing all the output as interested. Yeah. So this one I didn't. Sorry, I'm sorry that I didn't look into it very clearly. But yeah, the idea is just use the sum of the target output as interest and the related training examples as interest.
Yeah, I just feel that this paper is not so. Hello?
Yeah, it's not so what?
I feel this paper is not so strong.
Yep. You can argue that the way they calculate the contribute can get some problem or yeah. But for the application one they mentioned, I believe it indeed gives some potential understanding of how the model is activated and contributed. Yeah.
Okay, I just feel the paper is not so strong. We have we have other ways to do this. But the point of slicing the network is interesting. Because there's another PhD student, Sunny knowledge. So Huasong, right? Huasong is going to have his QE. So there, and he has the concern of that. One of the top topics is that how to reduce the sizing model and the testing accuracy.
Yeah,
so
I know.
Somehow this is relevant work to him. But I still have a strong concern that how this approach can really work and whether it is a trustworthy approach for him to follow. I'm still thinking about it. Okay, Wang Chao, please keep going on.
Okay, so the third, after the second and the third one, which I also think is not so important. Yeah, but so the idea is only encrypt part of instead of encrypt the entire model, it will select some important output they believe is to be important and then find the relevant
neuron
weight and the neurons to be encrypt, and then yeah, just like the selected output mentioned in application 2. So the idea is quite simple. Yeah.
And how they protect the slicing model?
How they protect? Yeah. So usually, how to encrypt the model is that the weight is encrypted by some homographic so it's by some, like it's the weight is encrypted by some key, and then to use it we need to first in the runtime decrease the key and then use its weight to compute the output. Yeah, that's how usually we do. But the paper process, instead of making all the weights to be encrypted, we can encrypt only part of them, so it will save some time. Yeah. And without this encrypted value, the model cannot be used.
But why don't they do, for example, authentication, but to encrypt the whole model?
What do you mean authentication here?
I mean, if you wanted to query the model, maybe if you just do a authentication for your identity.
Yeah, that's what is usually done in method 1. So I mentioned, so we run the model in a secure environment. But in many cases, we cannot run our model in a secure environment. We have to put on in a device, in a local device. So how to protect it locally is also a problem. So the way they propose is that instead of
I think this is a very
yeah, it's a very broad part to talk about as a standalone topic. So
do they have experiment for that? I guess not, right?
I guess there is, but so
this is the worst way, right? This is the worst way for
that. Let me see this. So, yeah, this is the model protection part, and this is how they protect the model. But yeah, but from my understanding, this part is usually not something because it gives very more references that is not what I know. It's far from what I know. Yeah, I only can get what they trying to do. Yeah.
So they do have some, but how they going to evaluate it? So the evaluation seems to be very strong.
So that's how they do. Yeah.
Okay, I think we should end your presentations because there's errands to go. So I have a quick comment here. So Wang Chao, I think you make a clear explanations about the core functions, but I think your slides is too brief in this case compared to your presentations last time, and also compared to Xiangling and the raw files within the slides. And their slides is more, I'm not going to use the word complicated, but their slides have more animations, have better organizations. So I suggest that in the future, when we have algorithms, we try to transform the algorithms into some animation because algorithms always have an animation. So you just understand some branch of the algorithms and you just mention in what scenarios and what are strategies. And that will be a better illustration for the algorithm presentations.
Yeah, but usually animation is harder than we draw it directly. Yeah, that's the problem. Yeah.
Yeah, and also for these presentations, you remove a lot of important experiment details. And
yeah, that's my bad because I think this too. So that's yeah, because in my thought, the idea is more important than its application. Yeah, so that's
in approach, I think the evaluation experiment is because for now when we organize these meetings, we're not just for not just this FYP. You should know that when you write a paper and Wang Chao, your work also have a good potential to turn it into a publication. So evaluations experiment, if you are for Xiangling and Ruofan, when we'll come that you know that experiments will be a paramount importance to decide whether to decide its acceptance. And for the paper we submit last night, and it is at 13 page. We spend half of the page writing for the experiment. So experiment is quite an important part. So next time I hope that we will have a detailed discussion of how to design an experiment. And even if we have achieved very good result in terms of model preparing stuff, and I would expect, so we need to find a lot of baselines to have a thorough comparisons and evaluations of our idea.
Yeah, can because usually so yeah, because I previously thought that the idea is the most important part. Yeah. So,
idea approach, I think that's very initial stage of research. Think idea matters, approach matters. But when you go to the stage, we usually think about experiment even before the approach. So sometimes when I think about research ideas, sometimes I always follow up how could we evaluate. And when we are working with Xianglings, now this the first step of now Xiangling is firstly going to inventing some evaluation measurement about visualization instead of propose our own. So that means we need to have a thorough understanding of the existing baseline approach. Okay, so I think we should call it days. But one part of this paper, we need to have some thoughts is that whether this approach really slices the model, or whether the neural network model is sliceable.
Okay, so actually, I got a second Q&A that I haven't asked. So the first I have already asked, and the second is that given a normal scene model, how to convert to a equivalent model structure that we can calculate the contribute. So I will give the answer directly. Is there's a method called image to column. If you learn CS5 to 4.2, you can know it. So it will convert a CNN model to a higher dimensional MLP. So after MLP, we can transfer it to the one model that we use in this model. Yeah.
And have they ever tried to retrain the model?
Yes, they tried. Yes, they tried, but they propose that even without retraining, so even after retraining, the result does not go up much. Yeah. So for example, the normal accuracy is 90%. After it's 87, and after
90% is accuracy after the slide
before
the model. Okay. So and how about,
for example, it's 90% for this label, it's 90%, and after slicing it's like 87. After retraining it's 88, something like this. So it will say that it does not need to retrain to get a very good result. Yeah.
You can directly convert it into MLP. Or
you may CNN? How?
I mean, how do you convert it?
It's called the image to column. You can search for this algorithm.
Oh, okay.
It's a high
MLP is
multi-layer perceptron. So it's a high dimensional MLP. It's not one dimension. It's a high dimensional MLP.
But some fully connected layer, something like that. Or
yeah, you can search for this if you are interested. And if you take 5 to,
I think Wang Chao, you can share these algorithms in the group and after meeting.
So it's quite simple actually. So it's better just search for it.
I suggest that you search and share in the group, and more people, you can save the effort of other people.
Yeah, can okay.
Okay, so I think I need to call and stop your presentations and good presentation skills, but I expected more detailed or beautified, a better, more informative slides, especially on the experiment part. And also, let's have some thoughts about whether the slides is really, of course, for an experiment, that's okay, but we still need to digest a little bit about the simple difference, the calculation of the relevance. We still need to have some thoughts about it. And I think a better improvement is that we calculated the KR divergence, then just calculate an average. So that will be more sound approach for that. Okay. Next one, Aaron. Hello, Aaron.
Hello.
Yeah. Will you please share the slides?
Yeah. Okay. Okay. So I start now?
Yeah, please.
Yeah. So this paper is about finding faults automatically while achieving high coverage with evosuite. So just an overview of what this paper is talking about. So we have a few methods of automating software testing, and all of them basically you're giving it a program as input, and as an output you'll receive a set of test cases. And there's like two main usage scenarios for automated software testing. So one of them is to find violations or specifications that the developer specified. So you can find violations, that means you found a fault. The other usage scenario is more common because developers usually don't specify these specifications, which means like they don't do proper defensive coding, like putting preconditions or assert statements. So it's hard to find violations of specifications that are not specified. So the second usage scenario is to produce a...
Wait a minute, my landlord actually is knocking my door.
Okay.
Hello?
Yeah.
Yeah, so someone is going to fixing some pipe. Okay, please go on.
Okay. Yeah. So the most common usage scenario is trying to produce a representative set of test cases that tries to capture the behavior of the program. So most search-based software testing tools, they just use code coverage as the objective function, and then you just produce some test cases, and then the developer is then supposed to add the test oracles from the test cases that the SBST produced. So one question that is not really explored is how suitable is SBST for exercising automated oracles. So in the first glance, SBST executes like a huge number of tests, and it has guidance towards the difficult program states using like the fitness function. But this might not scale up to optimizing an individual test input for each possible violation of an automated oracle. So recently, there is a research paper done that is to optimize the entire test suite instead of just optimizing individual test cases. And optimizing the entire test suite has shown to be advantageous. So this paper tries to optimize the whole test suite towards both goals, which is both the coverage criterion and trying to exercise the automated oracles to find faults in the program.
So here, will you please go back to the previous slide? So here, the specifications, they mentioned that one of the usage scenarios is that produce a representative set of test cases. So do they mention that on in their cases in these scenarios, they would like to, so the oracle is more like towards this representative set of test case, right?
Yeah.
Okay, well, please go on.
Yeah.
Mm.
So just a quick background on the different methods for unit test generation. So the first method is random testing, and basically it just randomly call functions with random inputs and try to satisfy the branches. So there's almost like no computation effort in choosing suitable test inputs. So this allows a large number of test cases to be produced in a short time. And this might be good because it can help to cover more violations. But it might struggle to cover parts of programs that are difficult to reach. So for example, this method add. So the thing about random testing is it can easily find a null pointer exception in the branch, because if you just pass null as the complex object C, then when you do C dot get value, there'll be a null pointer exception there. But then random testing has low chance of satisfying this condition because it requires an exact value of 1024. And so even if null pointer exception is thrown, we are still not sure whether this add method is functionally correct, because we are not sure if the exception thrown is expected or not. And this is because if you throw a null pointer exception, or if you throw this bug1 exception, both of these are not declared by this function. So you're not sure whether the null pointer exception is the expected behavior. So the second method for unit test generation is symbolic execution. So basically, you are assigning path conditions to program paths, and then when you solve one of the path conditions, it means that you are obtaining the test case to execute that path. And the goal is to explore all possible program paths. So for the same example, symbolic execution can easily generate the integer inputs to satisfy the if condition. In this case, it's the 1024, but it will struggle in producing an instance of this complex object. And then lastly, for search-based software testing, usually you have a fitness function where you encode the objective of the test generation, which is usually branch or code coverage. So one popular type of search algorithm is genetic algorithm, and SBST is applied to generate test sets covering the coverage criteria, which I mentioned. And so the test generation is attempted for one branch at a time, and it does not make use of test oracles. So because test generation tries to generate a test for each branch at the same time, it is unlikely to scale up to derive both a test input for a violation and also covering the branch. So for the same example here, we can see that for SBST, it can generate a test case to throw this exception. But the same problem applies where you're not sure if this exception is a real fault or not, because it is not declared by this function.
The point is that even if you throw the exceptions, it does not mean they actually capture the bug.
Mm-hmm.
So is that a point?
The point is that the main point is that there is no like the developer did not specify that this function is supposed to throw an exception bug1.
Yeah. Okay.
Yeah. So So I'm not sure whether the exceptions that you throw are whether expected behavior or not. So so now a test oracle basically it describes the correct behavior for a given input, and also like the procedure to compare it to the expected behavior. And so there's an oracle problem, which is basically saying that you have to manually add oracles. And so because of this, most developers don't do that. So we can actually just use like basic assumptions on programs to automate these oracles. So for example, obviously programs should not crash. So we can just check whether they are throwing undeclared exceptions. And we can use these unchecked exceptions as oracles. And another way we can generate these automated oracles is to check for contracts, which we will show some examples later. Yeah, so this is a problem that developers don't explicitly declare or thrown exceptions. So yeah, basically this is the same thing. The thing is, even though there are no null checks on complex object C, the programmer might already accept that a wrong usage can lead to null pointer exception. So it's difficult to judge if the null pointer exception represents a real fault or just a violation of an implicit precondition. So this paper introduces an extended fitness function for automated oracles. So firstly, we have a fitness function for the whole test suite generation. And this can be used in conjunction with a regular fitness function that targets code coverage. So firstly, we define this distance db comma t. So basically this is the distance of for a given branch in a given test suite. So obviously, if the branch is covered, the distance is 0, and then if not, we get the minimum branch distance for all the executions of that branch in the test suite.
So what does
it
mean that the prediction has been executed at least twice? So where is the prediction defined? Defined for the branch? Is the predicate is the branch condition?
Yeah, it's the branch condition.
And okay, so the point is that if the branch condition has been executed at least twice, what does it matter, and how does it make a difference?
Yeah, so they are saying that the statement has to be executed at least twice to avoid search to avoid the search oscillating between two values of the branch. So this part I'm not very clear about because they didn't really give an example.
So basically, if the predicate has been executed twice, then it will have a branch distance. Otherwise, it will just have the largest branch distance. Okay.
Yeah. And then we can have a fitness. So from this branch distance, we can have a fitness function for the branch coverage. So the big T is the set of all branches in the class under test. M is all the methods in the class under test, and MT is the subset of methods executed by this test suite. So the reason why they introduce this M minus MT is to reward execution of methods in the software under test that have no condition expressions, and which means that if there are no conditional expressions, then the method is more likely to be executed by T.
Okay.
And then from using this fitness function, we can we also try to keep track of the number of exceptions in the SUT that is not caught. So you only keep track of exceptions that are not declared in the method.
Wait a minute. Wait a minute. I will open the door. Hello.
Hello?
Okay, so the pipe of my room is just leaking, so someone is repairing it. And please go on. And there.
So the previous fitness function was the baseline fitness function, and now I try to keep track of the number of sections also. So this can be used as the automated oracle.
Keep track of the unique number of exceptions. So it's a number of exceptions, number of type of exceptions.
Right?
So the point is that they are. I have some confusions here. It's going to keep track of the exceptions not caught in the public methods. So it means exceptions defined in the private methods or protected methods.
So basically, if the exception is not caught, that means, for example, the previous example was if you apply a null parameter, then that function will just throw a null pointer exception. So since that function throws a null pointer exception, it could mean that there is some fault in that function because the exception was not.
Okay.
So we only keep track of exceptions not declared, because if it's declared, that means the developer understood that an exception was going to be thrown.
And some exceptions may be applied in the library, right? Was thrown by the library, for example, the socket exception or the fire not found exceptions. And those kind of exceptions is and it's a runtime exception. It will not handle this. So it assumes that it assumes that it only care about the exceptions defined in the library. And does the non-point exceptions consider exceptions not declared in method signature?
Sorry?
Does non-point exceptions fall into the category of the exceptions not declared in the method signature?
Yeah, it does.
And okay.
Yeah, but null pointer exception, they categorize it as not critical, which we will see later.
And for example, the arithmetic exceptions or divided zero exceptions, file not exceptions, all the exceptions are kind of exceptions not declared in the method signature, right? Okay, please go on.
So, for example, in this method, we also keep track of the explicit and implicit exceptions. So in this case, the explicit exception is the one thrown over here because the developer threw it himself. But the implicit exception is division by zero exception when x equal to 0. So that one is when it is not thrown by the developer.
Okay, so the explicit exception and implicit exceptions are actually so which kind of exceptions are they interested in?
Yeah, so the thing is they did not really.
So here I still have a confusion not declared in the method signature. So this is a method signature, right?
Yeah.
And for these signatures, whether this embedded argument exception has been declared.
In this case, it is not declared.
It's not.
You declare means over here it must say like throws.
Okay.
Yeah.
Okay. Oh, the point is that if the developers trying to throw the exceptions, so it means somehow it somehow implies that these exceptions it is expected to happen. Right.
Yeah.
Okay.
Yeah. So in this case, the invalid argument exception is not really a fault. So that's why undeclared exceptions is not really a real fault that they will consider.
So it only looking to the exceptions. So, but these throw exceptions, okay. So that means if it's throw exceptions, this branch somehow indicating the bug, right? So that means this branch should not happen.
Yeah.
Okay, please go on.
So, yeah, so the explicit exception is usually just because of undefined preconditions. So it's not really a real fault.
Uncaught. Let me go back to recap. So here is uncaught explicit exception. Is that an uncaught explicit exception? And the throw here is a declared exception, right? And the explicit exception is invalid. Implicit is divided by 0, and uncaught undefined person. So this is more, and this one, suppose x is 0, and here will belong to both the implicit exception and uncaught explicit exception.
Yes.
Okay.
Yeah. So now we combine both the fitness functions, or rather we extend the previous fitness function to get this fitness function for the automated oracles. So NE and NI is the number of unique thrown explicit and implicit exceptions. So we can see that we want to get test suites that will have the maximum number of thrown exceptions. So if NE plus NI is large, then the 1 over 1 plus NE plus NI will be small. And you want the fitness function to get to 0.
So the idea is that we would like to generate a test case to avoid both explicit and implicit exception.
No, to increase.
Oh yeah, to increase. Oh yeah, to increase those.
Because you want to find the faults.
Okay, the implicit exception. Okay.
Yeah. So as mentioned just now, all the thrown exceptions does not necessarily represent the number of real faults. Also because the execution of the test cases in the test suite, they could share one line of a software or one line of the code that caused all these failures. So, and this can only be determined through manual verification. So, and if you have two individuals with the same fitness, we pick the smaller one to avoid large test cases. Yeah, so they will be using this fitness function for the experiments later. And then another way to extend this approach and find faults is through testability transformation. So fitness function only rewards the number of violations of automated oracles found, but it does not provide any guidance towards maximizing them. So basically the SBST only tries to execute all the branches in the program. So now we can use testability transformation to add branches that throws exceptions. So these are the few different transformation techniques, and it all occurs at the bytecode level, but for the example, we show it in the source code level. So the first technique is the array access transformation, where we just include the out of bounds exceptions before you access an array. Yeah, so for example now, then the test case will be able to generate x less than 0 and x more than the length. And then the second transformation is division by 0. The third one is numerical overflow. The fourth one is class transformation. Basically just checking if the instance is null.
So here the problem. So this is giving this approach, the throw non-point exception statement is instrumented into the original method. But assume that this is a public method, right? Assume this is a public method, and when we generate a test case to test this method, we definitely will somehow create So this is export bar, right? This should be export bar.
Yeah.
Yeah, right. So I'm saying that it's still possible that we consider a test case which involve like test none, right? Because there's no prediction. So anyway, if we the preconditions to execute this statement is that the x is not none. X is not none. And when we generate a test case, as long as there's no guarding, there's no guarding conditions for it, it will definitely trigger the exception. And also, for example, when we are seeing the methods, especially this parameter is string. Suppose this parameter is string, and suppose we are passing some CQ expression. Suppose we are passing some CQ expressions, and it will definitely have a set of conditions to see whether the grammar of whether the expression conform to the CQ grammar, right? So if the string does not conform to the grammar, it will definitely to throw a lot of exception there. And when they giving what they did here, they will definitely generate X, which will throw a lot of exception. And in this case, does that make any sense? So sometimes it is so basically it assumes that the input is correct. The input is correct, and the program does not handle the potential input. But somehow the program, especially a program, is processing some command line, and every program will have its own definition of command, how their command look like, and it is very likely that if we test this command, we are going to generate the string conform to the grammar restriction. If the string does not conform to the grammar restrictions, then it will just throw exception. In this case, given their design fitness, does that means it will have intention to generate a test case, trigger those to construct the test cases with those incorrect grammar? So you can have I made myself understood? You should have a problem. Okay, so let me raise another example. Suppose let me write example. Let me write a test case like public. It's still a method, and it will string. It actually input a string s, and this string it has to conform to a lot of the restriction, like if s dot length should not is 0, it just throw exception, and if conform to certain regular expression, like match certain stuff, if not a match, it just throw exception, right? So in this case, we have two exceptions. First, if the string length is equal to 0, and then we will throw exceptions. And the second, if the string does not conform to certain regular expressions, and these regular expressions means a grammar. And if these expressions does not conform to the expressions, it will throw another kind of exceptions. And after this, and these two if conditions are actually the grammar checking condition, right? Unless these two conditions is conformed, then we're going to pass a lot of the logics here, and maybe the bug is here, right? And giving their fitness function. So do you remember that the fitness function is the number of exceptions? The number of exceptions plus coverage, right? This is the fitness function. And in this case, does it mean that the test case we're trying to to force the string, and giving here the test input is string, that this one will force the string to generate some this will force some evosuite to generate a string which incurs those exceptions. right? It will force the string,
yeah.
force the test case to enter the string. But these exceptions are actually fine. It's very fine to reach these exceptions because these exceptions are all these exceptions are intended exceptions left by the programmer. And it is quite fine that we raise those exceptions. And if we're going to reach these exceptions, it does not mean there's a bug.
Yeah.
Or does that mean that it is going to generate Oracle? So suppose it will consider the branch condition at Oracle. For example, it will force the test case to assume that the string should not, the string.length should not equal to 0. It will take these conditions as Oracle. I'm asking the questions because we are talking about generating the Oracle, right?
Yeah.
And how do they define the oracles and how do they extract expectations from the grammar or from the program?
They didn't really show any examples of it.
Okay. So here I think there's some very big, I think for the approach is very convincing that of course here x should not be none. And well, this x not equal to none will be taken as the oracle.
Yeah.
Okay. Maybe you keep going on and I just raise my example here, raise my question here. Please go on.
Yeah. The last one, actually I mixed up the labels. So actually this one is the reference access transformation. And this is the class transformation. So you just check that the class is correct. Yeah, and that's the last one for the test transformations. So another approach to extend
all these transformations are supposed to, we can find all those, the code of those transformations in evosuite, right? By right?
Yeah.
Those part of transformation should be has already incorporated in evosuite source code. Okay, please go on.
Yeah. And then the second technique is to use the generic API contracts. And basically there are contracts that can be checked on Java classes. So I'll show some examples, the table later. And in evosuite, we just check these contracts on instances of the class under test. And basically after every statement is executed, we check all the contracts for that instance. So these are the contracts that they use to check. And yeah, basically if any of these contracts is violated, it will mean that it will throw an exception, and it will mean that there might be a fault in the method.
So what does it mean for this contract? And does the source code include this contract?
Yeah. So basically these contracts means that that we have, so it's simple things like checking that for example, like A equals A is true. So if they check this contract and the instance is not equals to itself, then you throw an exception. So if this contract is not met, it means that something is wrong with the program flow. Yeah.
Okay, let me check those hash code. So the hash code should not restoring exceptions, and the method throws no undeclared exceptions.
Yeah. So the equals and hash code and toString method is the object.
Yeah. So I'm reading the JCE, the unexpected exception. So the method throw no declared exceptions. That is unexpected based on geocaching heuristic. Well, that's just what we discussed before, right? So the evosuite only checks the undeclared exception. And the no non-point exceptions is raised on method that receives only non argument. Okay. And how do they define a method receive only non arguments? And how do they know this method can only receive these kind of arguments?
I'm not sure.
Mm.
They didn't explain these contracts.
Okay. So the idea is that it's going to attract some general invariance of the program. So just more like incorporate some common sense into the as an assertion. So the goal is that they're going to generate a session there. Mm.
Yeah.
Mm. Okay, please go on.
So from this, they conducted their empirical study.
Mm.
So these are 7 research questions that they had.
Mm.
So firstly, they checked the number of undeclared exceptions found with evosuite. Then they want to check if SVST detects more exceptions than random search. So they use random search as like a control. And then they want to check if the testability transformation have any effect. And also they try to compare the effect of the contract violations and also the overhead. And then finally they try to check the number of real faults by using the assertions and object contracts technique, and also how many real faults you can find using the true undeclared exceptions. So basically they use the evosuite tool on the SF100 projects, which contains over 8,000 classes, and the on average the testability transformation adds 141 new branches per class, and the search budget was 120 seconds per class, and then they ran it 13 times to account for randomness, and then they also had this Ferga-Delaney effect size as a stats metric. So this is basically a test for symmetry to determine if there are as many classes with better results as there are classes with worse results. So a value of 0.5 means that so a value of 0.5 means that there are as many classes with better results as there are with worse results.
Well, how do they determine the better results?
Basically the number of unique exceptions thrown.
Unique exceptions. So basically they're more like instrument a lot of conditions, and those conditions are the guiding conditions for raising exceptions. So this Varga-Delaney effect size is more okay. So it's just make comparison. So how do you define the better results? So better results, does the better results mean that it will incur more exceptions?
Yeah, that's how they define it.
Okay.
Yeah. So for the first question is, we just check how many undeclared exceptions can be found with SVST. So they found 187 types of exceptions. So some of the exceptions found is quite trivial. So for example, the no class defined found error and the exception in initializer errors is due to interaction with environment. So for example, setting up logger or the IO methods, because it ran using a custom security manager, so it doesn't allow interaction with the environment. And then another Another exception is a headless exception, which is for GUI components because they ran it using Java's headless mode,
Using Java what?
the headless mode.
Okay, the Java headless mode. So that means, okay. So would you please explain more about the headless mode?
This one I'm not very sure. So.
Okay, maybe you can share the slides in the group, and then I can have a further check.
Yeah, okay. So these are the top 10 exceptions found. And you can see that the highest two is the null pointer and illegal argument exception, which is quite trivial. But the rest of them could mean that there is some real faults in them. For example, the array index out of bounds and the stack overflow error. So the second question is, does SBST detect more exceptions than random search? So from this table of results, you can see that evosuite outperforms the random search significantly in terms of the coverage and finding failures. So the number of types here is the number of distinct exceptions thrown.
Okay.
Yeah. And the number of execution is the number of distinct methods that throw exceptions.
Sorry for. Okay, please keep going on.
Yeah, so like the coverage here is better and the number of types of exception thrown is also better.
TT means the transformation, right? The testability transformation.
Yeah. So
and that means if we apply testability transformations, please illustrate more about TT.
Yeah, so that's the next research question. So basically trying to compare with testability transformation and whether it affects the coverage and exceptions found. So in terms of coverage, it is just a bit better than.
But their testability transformation is just adding more branch there, right? It's just adding more branch there. Those added branch will be counted. Here, the testability transformation is that when we find there the reference success, so it will add a branch to check if the reference is none, right? And then, so that means it introduces one more branch by testability transformation. So here the question is that when they count the branch coverage, will those added branch be counted as well, or it will not, right?
Yeah. So it's just the class under test branches. And the number of types, the number of distinct exceptions thrown is also more. But you can see here that like actually there are some methods that perform worse, but number of methods that perform better is a bit more. So there are more cases where it achieves better results than worse results. So you can see for the effect size for random testing is 0.40, which is smaller than 0.5. So it means that this algorithm performs worse. For testability transformation is just a bit better than.
So this testability transformation is going to compare with the genetic algorithm.
Yeah.
Right. So this just comparing. So that means the worse and better. So it means for the random testing, the J is better than random testing with statistic significance, and the testability transformation. If we deploy such a testability transformations, it is better than traditional approach with statistical significance, right?
Not.
That means it means that the J is better than randoms and TT is better than J.
Yes, but the TT is only a bit, just a bit better.
Okay.
Yeah, so they give some reasons as to why the effect size is not larger for the testability transformation. So one reason is due to you can only find additional failures if there was such failures in the SUT in the first place. And then second reason is that the search budget is the same for both methods, but there's an overhead for testability transformation. And lastly, it can be shadowed by the many classes that SBST cannot handle efficiently yet, which is the IO calls and the GUI components. Yeah. So the next research question is whether the contract violations work. So they found that most of the contract violations were due to they're related to just thrown exceptions, and all the contracts were validated except for EN, which is the equals to null exception, and the HN, which is the one that is checking whether the hash code is working. Yeah. So this is the average contract violations per class. And from here you can see that the testability transformation also gives more violations. And then this is the number of classes that exhibit that particular contract violation. Yeah, in this case, they didn't really explain much also on these results. Yeah. And then the next question is just checking the overhead of checking the contracts. So an average of 13% of execution overhead was introduced. So these are just the numbers that they shown. Yeah, so if they had to check the contracts when they execute each statement, then they can only execute lesser statements.
They executed a less statement per class within the time budget.
Yeah.
This overhead. So how do you define execution? Oh, it is execution overhead. So okay. So that means when we introduce those kind of instrumentation, is that those contract checking will be instrumented as well?
What do you mean by instrumented?
So you are saying checking contract, right? So when checking contract, you have compare A equals A to be true, right?
Yeah.
So that means if A is not equal to A, so somehow it will, if I understand it correctly, we will insert a condition or branch like if A equals A, else whatever it is. Like if it is else, we just throw an exception, something like that, right? So this kind of information will be also inserted into the class. Am I right or not?
I don't think they actually write the branches. They just do a check.
So if they do not instrument it, why it will incur 30% of execution overhead?
Because when they execute the test case, then like after every statement they will
do
will check the
every
contracts.
statement. They will
Yeah.
add. So well, the point is that then when generate a test case, they will add more assertions to check, and this assertion actually invoking the JUnit library, and this will incur additional runtime overhead.
Yeah.
Okay. But if we can find a bug, we don't mind to add this 10% of runtime overhead, right?
Yeah.
Okay. So the key point is that which part of the what part of the technique will allow us to find more bugs?
Yeah. So the next question is trying to see for the object contracts and assertions how many real faults can be found. So in this case, they claim that they found at least 477 real faults based on the contracts. So the main source of the real faults is when the contracts on the object methods are violated. For example, the equals method or the hash code method. And then also because there are some assert statements in the code which evaluate to false. And then most of the other faults that they found, they were just undeclared exceptions. So they did not classify them as the real faults. So you can also argue that the violations of assertions could be due to implicit preconditions. But they argue instead that if the developer made effort to write the assert statement, it is strange for them to leave the preconditions undefined. So they claim that having implicit preconditions could also be considered as real fault.
Okay, so for here, those 477 real for those real faults, and those implicit preconditions, most of the other faults found. So other faults does not consider as the real faults.
Yeah.
And argue that the violation. So and those violation of the violation of the assertions actually belongs to those real faults.
Yeah.
And they are due to implicit precondition.
So this is the part where they are arguing. So like yeah.
So I'm asking questions, yes or no. So the violation of assertions belongs to 477 real faults.
Yeah.
Okay. Okay. So and those faults are due to implicit precondition.
No, so they're saying it could be due to implicit preconditions.
Could be due to implicit conditions. And so now I'm going to raise my question. Suppose there's a method object O, and here I'm using O dot method 2. And when it will generate a non-point exceptions, will these exceptions be considered as the real fault in SF100?
I'm not very sure.
Yeah, so, but from my point, so suppose this O is non-point exceptions, it's very hard to say it is very hard to say it is a real exception because it expects the users will not passing the non-point exception here. Okay, please keep going on. Maybe it's okay because sometimes when I fix a bug, I always will fix NPE exceptions. Yeah, so but I'm not sure whether those 477 are all these kind of non-point exceptions. If that is, those real faults sounds cheap.
Yeah. So the last research question is how many real faults does evosuite find due to undeclared exceptions?
I'm really curious about this percentage. 95. Oh no.
No, so
Between
yeah, they found between 1,217, at least 1,217 classes with real faults.
with 95% of confidence level.
So
So
how do you get
does
this?
that mean the majority of them are undeclared exceptions?
I know. So as in they got this number.
Mm.
So basically they can only check if it's a real fault by manually analyzing it, and because there are so many classes, they only manage 20 such classes. They found that 8 of them have at least one real fault. So they extrapolate these 20 classes to all the classes with
Like 20.
yeah, and then they had some statistical analysis to show that these 20 randomly selected cases.
So in that case, it's very hard to say. You can see the majority of exceptions are non-point exceptions and the illegal argument exceptions. Do they have provided? Does the paper providing examples about non-point exception and illegal argument exception? Does there exceptions?
Yeah.
If they have a paper, but you do not provide examples here.
As in the examples that they give were just in words, which I can explain some here. Yeah, so for example, the illegal argument exception, they were all due to like missing truths declaration, but you cannot simply discard them as trivial faults because, for example, if method A calls method B with a wrong input due to a fault in method A, then method B might propagate the exception to method A. So actually, method A still has a bug because it generated the wrong input. And then for the null pointer exception thrown, is raised due to several different conditions. So first one is the parameter is null. Second one is when the method call on an object returns another object that might be null. And the third one is the constructor is called and sets some fields to null. So all these null pointer exceptions.
I think 2 and 3 might have a stronger indicator as the bug, but the first one, I really doubt it.
Yeah. So
is there a distribution for that?
No.
There are no distributions, but yeah, but for now, I think so. Here, I think we somehow can refine it because we once discussed because we only do the testing. Generating test case cover more branch, the definitely will be very useful, and we're working toward these directions. But we still have another stage that suppose you can see software testing is going to find a bug. So that is ultimate goal, right? Suppose and however, when we're doing some software engineering research, there are no so many bugs for us to find. So now we lower our expectations to generate test case so that we can exercise a lot of branch. So here, we're not working on the branch directly, we're working on the coverage. So there has already a lot of the researchers and argue that the coverage does not necessarily mean the branch, does not necessarily mean the bug, because a lot of branches are trivial, even if you can successfully cover those branches. And also covering the branch may not so easy sometimes. And when we cover this branch, we are not necessary to review the bug. So somehow, for now, but anyway, for doing research, coverage is an important indicator. If we cannot, having a good coverage is a lesser goal or an easier goal than finding a bug, right? In ultimate way. So if we cannot have a good coverage, then it will be more challenging to find a bug in automated way. So here, the capability of a high coverage is a facility, platform, or instrumentation, or sorry, the infrastructure. And when we have a capability of covering, so now we have the graph-based covering, so we can construct objects so that we can cover to more branch. And also we will proposing some flag method and flag effect to help us to cover more branch. But the ultimate goal is that when given a branch, we are going to cover this with very high efficiency. So that is the first goal. That means the branch coverage or the specific branch coverage capability. When we have this capability, we can use the similar tricks. For example, we can use these two heuristics. The first we're going to apply static analysis to see what kind of code is more likely to have bug. And then we can instrument the branch there and to let the code to automatically generate test case to automatically to trigger the potential bug. If we can trigger the potential bug, if we can make the inserted branch condition to be true, then we find a bug, right? So this is more like a cycle. The first stage is that we still would like to cover a single branch. So we are on this stage now. But next, when we are we're able to, of course, in this stage it's not easy. We need to instrument an additional branch. And when we have this capability, the next stage is that we're going to instrument more branches and to find the real bug later. Okay.
Yeah.
Okay, please go on.
So, two other types of exceptions thrown were Stack Overflow error. So, for example, the example that they found was they inserted a tree, a reference to itself, then which led to infinite recursion. And then,
but for this point, it's very hard to argue. So sometimes it requires the tree, or maybe So that might be a bug. So anyway, so whatever the input is, we should not let the program to have Stack Overflow error, right?
Yeah, and the last one was the array out of bounds. And basically, when the methods access with the set of get methods with no checks on the input.
Yeah. So later we might to think about. So at the first stage, we just still working on the publications. We have the graph-based seed generation approach, and we have the flag effect approach. But when those approaches are done, we are trying to apply our approach like evosuite to work on some open source project like Apache or some project else to find their bugs. Okay.
Yeah. So that's basically it. So to conclude, basically this paper presented an extension of SBST to exercise automated oracles and also produce high coverage at the same time.
And those automated oracles are in two parts. The first part is that we're going to instrument a lot of additional branch and exception there. And the second is that we are adopting some contracts and to add them as abstractions and try to find more bugs there. Okay.
Yeah, like what you said. And so there's a need for better techniques to filter out the false warning.
That is more likely that if they want to kind of experiment, they need to impressive data, like they found 477 bugs they find. But if they want to find so many bugs, they haven't have a very refined heuristics. So they try to report as many exceptions as possible, then they manually check them. In the future, if we would like to explore more, maybe we can think about a more sound, insert more sound branch, just like what I reported in the last the second to last slides. That we're gonna see what if a method, if they call a method, then to return none, whether such kind of non-point exceptions is more like a stronger indicator as a bug, or sometimes the stack overflow. But of course, there's no branch conditions to call in stack overflow. We still somehow need to construct think about a specific fairness to trigger this kind of bug.
Yeah.
Mm.
Yeah.
Okay.
And
Mm.
one improvement is for evosuite to also output annotations for test cases that throws exceptions,
Mm.
and also uh, the option to automatically add throws declarations for the developer if there are violations in the implicit
So here,
preconditions.
there are annotations for test cases. Throw exceptions. Option to add a throw to add it through declaration if the field is or not. It's very hard to argue that the violation. Yeah. Okay.
Yeah.
Yeah, but there still need to wait to check whether it is implicit precondition. Okay.
Yeah, that's it for this paper.
Okay, thanks Aaron. And I think all the students has left. So somehow I will try to find the other students who is more interested. And then later, I think the FYP, the new round of FYP is started. I hope we can find someone like you and someone like Zhang to work on this project. So that you have more companies. Of course, these meetings, for me, it has already taken over 3 hours. Some of the students, if not so motivated like me, have get exhausted already. Okay, thanks everyone.
Thank you.
And okay, please share your slides in the group.
Yeah, okay.
Okay, thank you.
Bye.
Bye.